All right. I'd like to begin with a visual judgment. Does everyone see that?
Yes, we see your
Good.
title slides here.
Yes, I'd like to begin with a visual judgment and basically to examine this portrait and decide if the people portrayed are siblings, sisters in this case, or not. And I think it should be a rather easy judgment. But let's go a little bit further, and I'd like you to assign either a measure of confidence or a measure of probability to it. Can you tell me, are you pretty sure? Or whatever. Okay. And the issue is, how are you making this decision? And this cuts across a lot of middle vision and even object recognition, higher level vision, as to how are you putting together information potentially from all over this portrait in order to make a decision. Okay. And we've been looking at this for some time. It's, I think, a novel judgment for visual neuroscience. But it's actually something of very great importance in the area of kin recognition, kin selection, and population genetics within biology. Also within computer science, deciding whether children go together with adults is sadly a very important question right now. And mathematically, it comes with the issue of Q combination. How would you put together Qs from different parts of an image? And how would you use that to play social games? So it's an area that touches on a lot of different research. If you're thinking about how you actually do the task, well, you might have started comparing feature by feature, or at least what you would call a feature, looking at eyes, looking across the two, and trying to come up with evidence that the two children are kin, are very close kin. Okay. And the thing here, though, is that while we could begin to try and develop a Q combination model, the odd thing here is that we don't really know the Qs. We don't know what the features are. We can say the eyes, for example, but it could be the shape of the eyelid as much as any. So what we're looking for methodologically is some way to manipulate images experimentally that will let us deduce things about features that are available in the face and how those features carry information about kinship. So basically, I'll talk a little bit about some results over the last almost 20 years concerning the features of kinship. We'll be using signal detection theory experiments. And in these experiments, you'll see a pair of faces, and you have to make a judgment as to whether or not they're siblings, whether or not they're, in this case, brother and brother. And we use that to assess D prime and criterion, and primarily D prime is going to be our dependent variable. So first question to ask is, where is the information in the face that contributes to kinship? How is it distributed spatially? And so looking at, in particular, this face up here, how much have you lost because there's a blue mask occluding the bottom half of the face? How much is your performance going to suffer? And there are three conditions in experiments: full face, just in this case, the lower half, and then the upper half. And we're going to basically be looking at these. Okay, to find out what happens when you mask. So the results are shown here, D prime, and then the three conditions shown horizontally. And you can see that D prime for the full face is slightly greater, but not significantly so, than D prime for the lower half. Whereas when you mask the upper half of the face, you lose essentially most, but there is a little bit of information still left in the lower half. Okay. And one conjecture for why this happens is not because there's less genetic dependence in the lower half of the face that could potentially provide kin recognition. It's simply that there's a developmental trajectory of for faces. And you know that children, when they turn age 12, start looking like horses. And they look like horses because the bottom half of their face elongates dramatically. And it may well be the visual system is simply sensitive to the fact that cues are unstable across age in the lower half of the face, and they're more stable in the upper. Okay. We can now continue doing this, looking at local regions, trying to essentially come up with the decomposition of information. And so what kinship information is available in the eye regions, the mouth regions, and the like? Again, a similar design, okay? And stimuli look like this. This is one condition up at the top, a second condition, and a third condition shown here. And we're going to compute the D prime for each of the conditions experimentally. Different subjects run in all three conditions. Okay. And we find that, of course, we get the full face. D prime is about 1. It's typically about 1 to 1.1 in these experiments. There's a slight reduction when we lose the eyes, but surprisingly little. There's still considerable kinship information available. And if we mask the mouth, if anything, we go in the other direction, and it's not significant. So in brief, we're beginning to develop a sense that the information is fairly widely distributed. Okay. Last, let's do the same thing, but this time horizontally. We'll lateralize the stimuli. The mask will go down the center here. And okay, we'll have a full face, left half and right half. You might stop to ask yourself what you expect. Now, some people have dramatically asymmetric faces. One of them is on the American $5 bill, the President Abraham Lincoln. He has a very strong asymmetry in his face, which you may not have never noticed until you look closely. But in any case, what we find looking at these conditions here is that basically it just doesn't matter. Now, this pattern of results takes a little bit of contemplation to work out the fact that if you hide half the face, in fact, you've lost almost no information. And so full face, right half and left half are essentially interchangeable, suggesting that genetically speaking, there's redundancy across the left and the right half. That wouldn't be true for recognition judgments, since if you have a tattoo on your left cheek, I will use it to recognize you over time. But it's not genetically coded, so it's not relevant to kin recognition. Okay. So the basic conclusion is we can gradually develop a map of where everything is in the face. Looks a little bit like this, where the orange part is redundant, and these are all D prime relative to full face. And we'll see another one of these a bit later. Okay. Next issue is facial inversion. Part of the information and one of the most powerful toolkits for face analysis is to invert faces because they behave very strangely. And this was noticed by Yin in 1969, but popularized by Peter Thompson in 1980. And it's called the Thatcher illusion. This is what happens when you're the British Prime Minister and you cut funding to the psychological sciences. They make up stimuli from you. Okay. And so you've all seen this, essentially, that we seem to notice or not have access to the features in the face when it's upside down. This is a remarkably universal pattern. It's true for recognition of individuals, emotion, Thatcher illusion, gender, attractiveness, trustworthiness, intelligence, and so on. Age is perhaps the only exception because people may use skin texture to judge age. So, what happens when we invert faces, but we ask you now to judge whether we're looking at siblings or not? All right. So, here are the conditions. There's two ways to invert a face, which you know well from Photoshop commands and also PowerPoint. So we did both. We flipped horizontally or we rotated. And that's it. Basically, there's no difference at all when you invert a face in kin recognition, unlike every other facial judgment that's been tested. So we're looking at this and trying to make sense of why this should be so, why this one particular cue is insensitive to orientation. And last, basically, we'd like to develop a model that would allow us to cut up the face into and basically find out where the information is, and also whether, if you look at two regions, you have additivity. So we're testing additivity, and to do that, here, okay, we're going to be using stimuli where there are three conditions, and two conditions have complementary masks. Now, this little thing down here is a mouth, and this is a face missing that mouth, and this is the full face. So we're testing whether we're going to get additivity of information in going from mouth to basically not a mouth to full face. And we can check for additivity by converting D prime scores, roughly speaking, to Shannon information. And this is an approximation due to Peter Killeen. Okay. So we're going to see if Shannon entropy derived from D primes is additive. And this is what the stimulus conditions look like. We're going to mask the mouth here. And do they behave as statistically independent cues is technically what we're looking for. Okay. And one possibility is that masked regions, in fact, are additive. So they behave like independent cues, just like typical cue combination. Alternatively, it could be that there is more information in the features than you can extract from the face when the features are present in the face. In brief, the face is hiding or masking the information when it's there. And the opposite of that is holistic perception, so-called, which has been suggested as characteristic of face perception, that the features are enhanced and more informative. And the brief answer is no. Basically, it's not holistic. It's not additive. And it seems almost as if it is difficult, if not impossible, to extract all the information in the face that you could get if you examined the features in isolation, which is, again, an intriguing result. I'm afraid I have more questions than answers in this talk. And that brings us to the end, which is the same is true when we mask the eye and use the complementary region to the eye. And maybe to just leave you with a whimsical example, this is Baroque painter Arcimboldo, who was at the court of the Holy Roman Emperor and did portraits like that. It's hard to see the fruit when the face is there. Done.
Oh, very interesting.